Stefano is going to basically fill you in now in the break, and mine is more going to be later during the
Okay.
So, Stefano.
Okay. Good morning, everybody. So I want to talk about a little bit some idea about FFT data distribution that I have implemented in my version of Quantum Espresso. It's not yet in the trunk, but basically the idea is that, as Paolo said, has shown, there are many levels of parallelization in Quantum Espresso, starting from the basic real space and G-space distribution, and then you go on to K-point, actually bands before K-point, and there are also task group, and then there are additional things. And the problem is that one problem is that some of this level of parallelization may interfere. For instance, the band parallelization may interfere with the task parallelization and with the FFT parallelization, because basically they all deal with the same wave functions that are distributed differently in the different, for different tasks, for different properties, they are distributed differently. So, just to quick reminder to something that everybody should know probably, but okay, data are typically distributed. We have, I don't know, projectors, we have wave functions, we have each of these objects is a big array that is distributed across processors, and each processor has a number of plane waves. Only a small number of plane waves, and then whenever we do operation locally, and then we communicate, and so that we do, I don't know, MP sum or something like that, so that the result is distributed to all processors. This is, let's say, the main distribution of plane waves across processors, but actually the one tricky thing, one important thing is that this is, how this then is dealt with when you have to move from reciprocal space to real space. We have some indexing that basically bring the plane waves from the array containing the Fourier component of the wave functions or projector or whatever, to we map them into the FFT grid in reciprocal space. And this is actually mapped on columns along z directions. And then these columns along the z direction are Fourier transform in one dimension. Along the z direction, you can do a Fourier transform. So you get an object which is in reciprocal space on the first two indices. Then you have an FFT scatter, so an all-to-all MPI call that redistribute this data in such a way that, again, you have data that are classified by G, X, GY, and an RZ, but here you had all the RZ component for a selected pairs of GX, GY. Instead, here you have some slices, so some slices for some RZ, but you have all the GX, GY. And then at this point, you can do a 2D FFT in X and Y, and then you get basically each processor has slices of the object in real space. Nice. How does it scale? Well, it in principle scale. There are two components in the scaling, no? Because basically you have to do some work, but distributing the work across processors. So let's say that you distribute some task, and so then the work goes like decrease with the number of processors. However, you have to send around messages about what you have done. When we do the all-to-all communication, then you basically, each processor has to communicate to all the other something that has a latency and some bandwidth. And so eventually, if the number of data, so if you write down how it goes, the communication time grows with the number of processors. The number of data decreases with the number of processors because you have less data on each processor, but eventually you pay mostly the latency, and the communication time is proportional to the number of processors that are involved. So for a large number of processors, communication time tends to be dominated by latency. So this, I don't know if we are already, depends on the system when this set in, but eventually it will happen. But another problem that we have is that actually the way things are organized is that we need to distribute plane of the wave function or the density or whatever. So we need then the amount of number of processors that we can use efficiently is limited by the number of by the third direction of the grid. And so if when we have more processor than plane in the FFT, then we get in trouble, and this is why we go to use the task group whenever we can. But if you want to use, for instance, conjugate gradient diagonalization, which act on one wave function at a time, then you need to use only one wave function. You only one, yes, you do one wave function at a time, and so you cannot use a task group, or you are not using efficiently the task group. So there are many parallelization strategies, but let's say band group parallelization, in which you assign certain tasks to a group of processor, you assign a group of bands, interfere with task group, because task group does exactly the same thing for the FFT. And and certain operation like conjugate gradient diagonalization, for instance, doesn't really use, cannot really use band parallelization. It could be possible, it could be useful to have a different distribution of data in real space and G space in order to improve scalability. So that was the idea. So how? Okay, this is what we had before. We actually can distribute fraction of planes. I mean, it's not a very smart, I mean, not very original idea, but instead of distributing, instead of having full planes distributed in real space, we distribute partial planes, okay? So then we can basically have, in the limit of very many processors, we can have basically one partial plane per processor, and this should allow to scale to a larger number of processors. How do you do that? Well, okay, in principle it's not difficult, but basically okay, how do you do? You decompose further. Instead of doing 1D FFT here and 2D FFT the second time, actually you do 3 one-dimensional FFT. When the first you do the same, for the first you do the same, but the columns that you need to, I mean, that you assign to a given processor have to be arranged in such a way that they belong to the same a certain limited number of plane along the x direction. I mean, in the in the YZ direction, so orthogonal to the x direction. So basically, one can have a group of processors that own all the columns that are in some of these, I don't know, lightly colored planes, and then another group of columns that are owned by processors that will eventually have these more intense colored planes. You do the FFT along Z, then you scatter inside this group of processors in order to get the data on the YZ-oriented planes. At this point, you have all the data in Z, but also all the data in R, and so then you can, in Y, and so you can do a second one-dimensional FFT along Y, because all the data are local. Then you can scatter again in a different group of processors, the orthogonal group of processors, and now you are basically mixing all the, let's say, red, but you redistribute the red data from something which is oriented in the Y direction to something which is oriented in the X direction. And then at this point, you have all the data for the same, with the same, I mean, you have all the data for all the Rx, and then you can do the last FFT. So in this way, basically, you can perform the same procedure, but doing two FFT all-to-all communication on smaller group. Is it convenient or not? Well, the point is that, at least should be, theoretically, this is the idea, that the computational time should go away. I mean, basically, if you have many processors and you divide the processor into in an array of processor, which is in a square, in a matrix of processors, so that which has certain number of processor on the as row and certain number of processor as column, then the computational time decrease with the number of processors, so this should become small. You have to do twice the communication, but each of them is done on a smaller number of processors, and because the total number of processors is the product of these two. So basically, ideally, if you have a very large number of processors and you can exploit this fully, the communication time should grow like square root of the number of processors rather than the number of processors. And what is more important, and probably is becoming more important before actually the timing is all dominated by the latency. But what matters is that now you are limited to NP1 and NP2 to be less than, respectively, NR3 and NR2, because these are basically the limits that you have. And so this should allow to scale to at least an order of magnitude more processor, hopefully. So this is it. So the hope of these things was to get rid of the task group parallelization, because task group is invasive and not very clear what it does, at least not to me, up to recently. And so I hoped to get rid of it. You can't really do that. because the task group parallelization is more efficient. It's more efficient because it communicates bigger chunks of data less time. Because from the point of view of the calculation done, it is the same. But basically, task group. So what I'm saying, we have we have the wave function at so let's say we do the FFT along Z, then we scatter, then we do the FFT along Y, then we scatter again, and then we do the FFT along X. On top of this, or in the old scheme, we were doing an FFT along X and Y, and that was it. But in order to do that, we could do efficiently this only if the number of plane along Z is large enough. What task group does is that you have many wave functions, and then you scatter this wave function. So you reorder the wave function. So you pack the wave function in a smaller number of processors, and then you do this, and you do the FFT in this smaller number of processors. So when you do this, basically you do one communication more, but if but possibly you are collecting all the wave function on a single processor, and then you can do a local three-dimensional FFT, or anyway, you can pack them more efficiently so that the initial scatter, I mean the the FFT scatter is efficient, and you are doing fast Fourier transform. You have full planes for each processor, because the problem of having more processor than planes is that otherwise, if you don't do this, if you don't pack the wave function, then you have basically processors that are idle. The advantage of the task group parallelization is that it does this collection of, in a certain sense, it does the same. I mean, we can redistribute data here, or we can redistribute data here, and basically, and the amount of calculation in the end is the same, but what happens is that if you do this, you distribute bigger blocks of the wave functions less time. Eventually, you call the FFT less time. And so this eventually is so I couldn't get rid of the task group eventually. But one thing that this distribution of data allows is actually to perform this second, this distribution also when you have only one wave function, so when you use conjugate gradient, for instance, or also for the density, also for the potential. For this system, for this other quantity, you can't use the, we are not using the task group because we deal with one density at a time, and so we can't do that. So the idea is that to merge the two things, and so to have basically something which is, call it task group, call it as you like. If you have many wave functions, you do this, you scatter here, and you collect the full plane, so that you don't need to do this gather scatter. If you only have one wave function, or you only deal with the density or whatever, then you don't have these things, but you distribute the data in such a way that partial planes are distributed. This is the idea, and this I implemented in. I mean, it's not in the trunk, but I did it in PW. It works in PW. It works in the phonon. Is not working in Carparinello, so I need to find out why. But it works for many of the processors, processing things. So this is something I'm working, and I would like to put in the distribution as soon as I can get rid of it. Once this is done, one other thing that is annoying is what happens when you do we do gamma point calculation. When we do gamma point calculation, wave function are in real space. So I mean, wave function in real space can be taken real, and this is an advantage that we don't want to give up, and so this makes that actually we try to do 2 wave function at a time whenever possible. I mean, in Carparinello, everywhere, and in PW, in many places, there is this option: if real, if gamma, then do this; if not gamma, do that. And the same stupid 3 lines of code becomes several options repeated and slightly different each of. Okay, so if this is true, that we don't want to lose this advantage, but if doing the FFT of a real function would cost half doing the FFT of a complex function, then we don't need that. We simply, pay half. We do each wave function one at a time, but we cost and so the code would be much more simpler. And we can, because what we have to do is, what we have to do, we have the sphere in the G space, and we only have the positive G, which means only half of the sphere actually. So when we do the FFT along Z, we only need to do the one-dimensional FFT along Z for half of the columns. So if the complex case costs 1, the real case would cost 1/2. Fine. Then we have something which is full. Okay, so we have what do we have? Many Z. Okay, and then we need to do the FFT along yeah, exactly. So we have to do the FFT. So we have done this. So we have a cylinder basically in this half of a cylinder, and then we need to do the Fourier transform along Y. In principle, in the usual case, we have the full sphere, and so then the FFT along Y would cost 1 again. But here we have only half of this cylinder, so this will cost half again. And then when we do the third FFT along X, what we have we have half of the cube, but now we want to make the Fourier transform along x. And so then we would say that this we can't gain anything because, I mean, then we have to do all of them. So then this would say that the complex calculation would cost 3, let's say in some unit, and the real space calculation would cost 2, which is better than 3, but is not 3/2. However, what do we do when we do the FFT in real space? We take two wave functions that we know will be real once transformed, and we combine them in such a way that we get the real part is one wave function, the imaginary part is the other wave function. Okay, we don't have two wave function here, we have only one wave function, but we have millions of rows. Each of these rows has to be real once we have transformed them. So we can take two of these rows, pair them, Fourier transform them along y, with the same trick. I don't know exactly how, but I'm sure it is possible, with the same trick that allow us to do two FFT of two wave function, and then disentangle the two wave function in real space, taking the real and the imaginary part. The same trick applied to the rows will allow us to basically do two rows together. And so this is going to be 1/2. And so this is going to be 1/2. Once this is done, if this is done, then first we don't need the NLM array anymore. We don't need this. We don't need to distribute the columns, the positive columns, and whenever we distribute the positive columns, we need also to distribute the negative columns that goes together, which is something that is an additional constraint that doesn't help in distributing the columns in a more efficient way. So I hope that things will be also more efficient, and there will be some data that maybe we don't need anymore. But for sure, the code should be much, much simpler, because we don't need anymore to do two wave function at a time. We simply need to say this is one wave function that is going to be real, and so we call another flag in the calling of the routine that knows that this has to be treated as a real wave function. That's it.